Hello everyone. In this video we're going to learn about rational expressions and functions. We're also going to learn how to multiply and divide rational expressions. Now if you recall, a rational number is a quotient of two integers. The set of rational numbers is a subset of the set of real numbers. So we start with the simplest numbers, which are just whole numbers and their opposites, which of course includes a zero as well, the set of whole numbers. So when you look at all the nice simple numbers, we call that set the set of integers. So the set of integers is basically z equals ... -3, -2, -1, 0, 1, 2, 3, etc. So the set of all these simple numbers on the number line, whole numbers and their opposites, is called the set of integers. Now you take any two of these and make a quotient and you end up with a rational number. The only restriction is we should not have 0 as a denominator. Otherwise, no other restrictions. Except the fact that both of them need to be from this set, the set of integers. Now, a rational expression is the variable version of rational numbers. So it's a quotient of two polynomials. Just like a rational number is a quotient of two very well-behaved and simple numbers, a rational expression is a quotient of two very well-behaved and simple expressions known as polynomials, which we have introduced previously. So these are examples of rational expressions. And you may wonder, what is this doing here? Shouldn't this be up here? Remember, a simple number like 1 can also be considered a polynomial of degree 0. So 1x to the 0, for example, you can write it as. Same with 3. So even a simple fraction like this can be considered a rational expression. We would consider this to be a constant rational expression. So as far as introducing rational expressions as a function, we can just define them in this way. We can say a rational function is any function of the form r of x equals p of x over q of x, where p of x and q of x are polynomials. And of course, we don't want the denominator to be 0. So we exclude from the domain of R any x value that would make q of x 0. So to explore that notion further, recall that the domain of a function f of x is the set of all acceptable values for the input variable x. And in other words, any value for which f of x is well defined. Also recall that any fraction whose denominator is 0 has an undefined value. This means we have to be careful when working with rational expressions and functions and make sure the denominator of a rational expression or function is never 0. When we want to find these problematic values of the variable x that would make this undefined, there are two ways in which we could state this. We can view this as simply a rational expression, in which case we'll just say what are the values of x that would make this undefined. Or we can talk about it as a rational function, in which case we bring in the language of a domain. So just to find out what x values would make this rational expression undefined, recall that all we have to do is we have to find out what values of x would make the denominator 0, this polynomial that's in the denominator position. So all we have to do is set 3x minus 2 equal to 0 and solve for x. So we get x equals 2/3. So any value of x is okay to plug in as a substitute value in this rational expression, except for 2/3, because if you plug in 2/3, you get 3 times 2/3. The 3's cancel out, you just get 2 minus 2, which is 0. So that's why we do not want to use the x value, which is 2/3. So the answer, find the values of x that would make this rational expression undefined, would simply be x equals 2/3. Now, if you want to speak in the language of functions, you don't state it in this way. You just say, what is the domain of this rational function? And of course, the domain would be any real number that would not make this expression undefined. And as we found out up here, the only value of x that would make this function undefined is 2/3. So we state it in this manner. We say the domain is the set of all x belonging to R, meaning all real numbers, such that x does not equal to 2/3. So we can also state this. Now, if we look on the number line for a graph of not the function, but the domain of the function, it would include all real numbers except this one number 2/3, right? So the domain would be what we've just graphed here. So in interval notation, we can say, we can take and describe this piece, which is -infinity all the way up to 2/3. So we say open interval -infinity to 2/3. And remember, we want to use parentheses because we don't want to include the 2/3. If we wanted to include 2/3, we would have used a bracket. And then we want to put that together with, so union, that's the operation we use here, all real numbers, in other words, to the right of 2/3. So that would be all real numbers right after 2/3. So when you put parentheses 2/3, that's exactly what that means. And all the way to infinity. Notice in set builder notation, we could have also said this. We could have said all x belonging to R such that x is less than 2/3 or x is greater than 2/3. Notice in this way, we're only leaving out one number, namely x equals 2/3. So this is less common. We usually write it like this. And the most common form, which we'll use in more advanced math classes, of course, is the interval notation. So you want to make sure you can handle the interval notation. This notation is called set builder notation because you don't actually put all the elements of the set in there, you describe them. You basically give instructions for how to build the set. That's why it's called set builder notation. So we're going to do the same thing here for this rational expression and then state the domain of the associated rational function. So basically, remember, we're not worried about the numerator becoming 0, we're worried about the denominator becoming 0. So we're going to go ahead and set the denominator, x squared plus 5x plus 4 equals 0. Then we can factor it. So we get x plus 4 times x plus 1. Notice first times first is first, last times last is last. Inner product is 4x, outer product is x. They add up to 5x. So it's a correct factorization. Then we apply the zero factor property. We set each one of these equal to 0. So this has to be 0 or this has to be 0. So x equals either -4 or x equals -1. Now we will want to avoid both of these x values because they would make the denominator 0. So the answer to the first part would be x equals -4 and x equals -1. Now we'll use this information to actually write the domain of this rational function. Any rational expression can also be expressed as a rational function. So now we say the domain is all x belonging to R, meaning all real numbers, such that x does not equal to -4, -1. And now we've described this domain. Again, if we look at the domain, right, it's going to be all real numbers, but with two exceptions. -4 and -1 are not part of it. So basically, we want to describe all the real numbers. Notice, of course, these pieces are on the number line. We just draw them a little further up to make it easier to see, but they're actually on the number line. So if we describe it using interval notation, we'll start from -infinity and go to -4. So -infinity to -4, stop there, but don't include -4, right? Union, then we want to include this piece, which is all real numbers between -4 and -1. So that's going to be open interval -4 to -1, union -1 to infinity. Like so. All right. Make sure you can handle both of these questions before we proceed. All right, so here we have another problem. We want to find all the values of x that would make this rational expression undefined. So remember, we're going to set the denominator equal to 0. Now, if you solve this for x squared, you get x squared equals -4. What real number do you square to get -4? See, there is no such real number, right? If you square 2, you get 4. If you square -2, you also get 4. So there is no real number you can square to get -4. So there is no value of x that's going to make this rational expression undefined. So you say, oops, here we go. So you say no such x here. Now, so what's that going to do as far as the domain of the associated function? Well, that means the domain is not going to have any real numbers excluded. So that means the domain is the set of real numbers. Sometimes you may see it written like in words, all x such that x is a real number. Or you can see it in interval notation where you just say -infinity to infinity, like so. Next thing we want to look at is how to simplify a rational expression. The principle that we used to simplify regular fractions, if you recall, was what we call the cancellation property. For example, when you take something like 10/25, right, and you reduce that, basically what you're doing is you're saying that's 2 times 5 over 5 times 5, and then that's going to be 2 times 5 times 5 over 5, which is of course the same as 2 times 5 times 1, and then you end up with 2/5. So of course you don't show all this, do you? You usually just do this. You just go 10/25, 5 goes into 10 twice, 5 goes into 25 5 times, equals 2/5. But it's important to know that these are all the steps that we're taking for granted when we do this. So this is the real reason why this works. So In general, we say if we have AC over BC, that's going to equal to A over B. We're basically canceling the C's. Once again, just like we explained here, the reason this works is because we can take this and split it up like that. That's just by definition of multiplication of fractions. And here we know that any number goes into itself once, so that's going to be 1. So we get A over B times 1, which is A over B. So this is called the cancellation property, and it is the same property we're going to use to simplify rational expressions. Now, it is extremely important to understand that the cancellation property works, we're missing an S here, only when the numerator and the denominator are both composed of factors in products, like this. That's a product, these are factors. Product, these are factors. You cannot use it when either the numerator or the denominator contains more than one term. Or both, of course. But even if one of them, like here, notice this is just one term, but this one has two terms, you cannot do this. And here, again, these are two terms, you cannot cross-cancel. You can only cross-cancel when the only operation in either the numerator or the denominator is multiplication. Be very careful not to do this, okay? So here we're going to go ahead and simplify these. What we'll do to simplify this is we're going to use a very systematic approach. We're going to go ahead and find the prime factorization of 144. We know that 2 goes into it 72 times, 2 goes again 36 times, again 18 times, and once again 9 times. Now we have to go to 3, which gives us 3 times, and then finally 3 gives us 1. Once we get to this one here, we have the complete prime factorization of 144 on the left here. And we'll do the same thing for 224. We know that 2 goes into 224 112 times. It goes again 56 times. Once again 28 times. Again 14 times, one more time 7 times, and then finally 7 1. Here we have the prime factorization of 224. So we can write 144 over 224. Lost my whiteboard there for a second. In this way. For 144, we're just going to write 1, 2, 3, 4 factors of 2, 2 factors of 3. For 224, we're going to write 1, 2, 3, 4, 5 factors of 2 and a 7. So now we just cross cancel. This cancels this, this cancels this, this cancels this, this cancels this. And that's all the cancellation that's possible. The beauty of this prime factored form is that leaves no doubt whatsoever that there is no more common factor that can be gotten rid of. So for the final answer, we'll just get 9 over 14. We can quickly verify that by just for some reason my whiteboard doesn't want to stay in place today. All right, here we go. So if you just go 144 divided by 224, oh, It's not working as I was hoping. All right, so we'll just hit enter. So we get that. And if we type in 9 divided by 14, the moment of truth, the exact same number. Okay? So, of course, we didn't have any doubts. We weren't checking for that purpose, but it was just nice to see your result in action. The fact that this fraction and this fraction have the exact same value. So now we can do the same with rational expressions. So we're going to go ahead and factor both the numerator and the denominator as much as possible. I look at the numerator and I don't see any factoring possible, right? But I don't know why I made that so big. I don't really need it that big. Okay, and I look at the denominator. I do notice a common factor of 4. A GCF of 4 here. We factor it out. That leaves us x plus 3. Now, okay, notice that this kind of cancellation where I cancel the x and the 4x and leave a 4, cancel the 3 and the 12, leave a 1 here, 4 here, would be completely wrong. Remember, you never cross cancel terms. You only cross cancel factors. But now that I have factored the denominator, I can cancel out the entire, see, I wouldn't be able to cancel just x or just 3. But I can cancel out the entire x plus 3 there and the entire x plus 3 down here, because here x plus 3 is a factor that's being multiplied by 4. So that leaves me a 1 and a 1. So now I end up with actually, I end up with 1 over 4. And that's all that's left. And that's perfectly correct cancellation right there. All right. How about these? Remember that you should be able to handle these. So pause the video, try them on your own. You're just going to factor the numerator as you know how. The denominator, you should know how. And the same thing here. Factor as much as you can, then cancel as much as you can. So we notice here, now that you're back, that we can factor out an x on the top, and that leaves us x minus 4. And downstairs, we have a trinomial factoring situation. So we know we can have x. By now, hopefully, you're more comfortable with these. First times first is first, last times last is last. Inner product is negative 4x, outer product is negative x. They add up to negative 5x. So now, notice we have factor, 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 factor. These three are what we call binomial factors, but nevertheless, because they're being multiplied, they are factors, which means what? Which means we can legally cross cancel. And we are now left with x on the top, x minus 1 on the bottom. And of course, we fight any temptation of the mathematical devil that would tell us to cross cancel those. We know better than that. We can never cross cancel when there's more than one term, either on the bottom or on the top or both. All right, so here on this one, we know that we can factor the denominator, right? Because that's the difference of squares, right? So we get x plus 2 times x minus 2. But that's all we can do. See, that does not leave any factoring, that canceling that's possible, because there's nothing we can do with this sum of squares. Remember, sometimes with sums of squares, like let's say we have 4x squared plus 16, sometimes you can at least take out a common factor like that. But here, we don't even have that, right? The GCF is 1. So there's nothing we can do with x squared plus 4. So we leave it alone, and this factorization didn't do us any good. So in fact, with a problem like that, we just box it and we say it's already simplified. As simple as it can possibly be. Try these two before you come back to the video. It's all about factoring. I told you when we started to learn factoring, if you know factoring, you're going to be fine the rest of the way this term. If you don't learn factoring, we're going to have very, very big problems. All right, so we notice on the top, we have a difference of two squares. So we're going to get u plus 3 times u minus 3. Down below, we notice that you should recognize that. You see, that's a perfect square, that's a perfect square. So f would be u, l would be 3. So negative 2fl is negative 6u, which is the middle term. So that's a perfect square trinomial, right? But if you didn't notice it, you can just factor it like a regular trinomial. So you get u minus 3 minus 3. Eventually, you would see that it's a perfect square trinomial. First times first, first. Last times last, last. Inner and outer add up to the middle, okay? So now we notice that we can cancel the u minus 3's here. And that's it. So we're left with u plus 3 over u minus 3. And as you know, that's all you can do because we never cross cancel terms, right? This is as simple as this is ever going to get. All right, so I do hope you tried the next one as well. We notice up here, we have a common factor of 3v squared, right? That leaves us v cubed minus 8 once we factor it out. Down here, we have a common factor of 9v cubed. When we factor that out, that leaves us v squared minus 4. Right? Try it. Multiply this out. You'll see. You get this, right? So, difference of cubes, difference of squares. For difference of cubes, of course, we need this rule, f cubed minus l cubed equals quantity f minus l times quantity f squared plus fl plus l squared. For difference of squares, we need this rule, f squared minus l squared equals f plus l times f minus l. For this difference of cubes scenario, our f is being played by v, and the role of l is being played by 2. Because that's 2 cubed, right? So v cubed minus 2 cubed. For the difference of squares scenario, the role of f is being played by v as well. And the role of l is also being played by 2. So we're going to apply this rule with f equals v and l equals 2. So we get 3v squared times v minus 2 that's f minus L, v minus 2, times quantity v squared, which is f squared, plus, now multiply f and L, so we get 2v, plus, go ahead and square L, so you get 2 squared, which is 4. Down below, we have the 9v cubed. We go ahead and factor v squared minus 2 squared, right? So v plus 2, v minus 2. Quantity v plus 2 times quantity v minus 2. We notice that we can cross cancel this v minus 2 and that v minus 2. We notice that 3 and 9 leave us 1 and 3. V squared and v cubed leave us v. Remember how we learned how to cross cancel powers with the same base as long as they have positive exponents. That's safe to do. Okay, so after the cleanup, we're left with v squared plus 2v plus 4 over 3v times v plus 2. If you recall from when we discussed a difference of cubes formula, I told you this part is not going to be factorable over the set of integers. So we'll leave this part alone. That's going to be prime. So since there's no more cancellation, we can leave the problem like this and answer it, or we can distribute the 3v to make it look a little nicer. So we get v squared plus 2v plus 4 over 3v squared plus 6v, like that. Both of those are acceptable forms of the answer. Now there's one case, we call it the f minus L over L minus f case. Sometimes they call it the a minus b over b minus a case. Doesn't matter. It's that these two are the same terms with the subtraction order reversed, right? So like 3 minus 9 over 9 minus 3, right? Notice you're going to get negative 6 up here, and you're going to get 6 down here, so we end up with negative 1. Look at another example. 11 minus 4, 4 minus 11. You get 7 up here, you get negative 7 down here. We need an equal sign here, so we get equals negative 1. In general, if you have f minus L, you can write it as, I was not in a typing accuracy mode when I typed this up, when I made this particular document. All right, so in general, we note that if we have f minus L, we can write it as negative L plus f, factor out the negative, it's actually a negative 1, right? Which leaves us L minus f. In other words, f minus L is the opposite of L minus f. We've seen it in action with some actual numbers. Now here it is as a proof. And L minus f, we can write it as negative f plus L, factor out the negative, that leaves us f minus L. So oppositeness is a mutual relationship. If f minus L is the opposite of L minus f is also going to be the opposite of f minus L. So anytime you have this kind of a scenario, they are going to cross cancel, but with a caveat, right? It leaves a negative 1 behind. So whether you write f minus L as the opposite of L minus f and leave this one alone, they cancel out and give you negative 1, or you can leave f minus L as is and replace this, the L minus f, with the opposite of f minus L. Same thing. They cancel out. 1 over negative 1 is negative 1. So we can cancel anytime we have this scenario, but always remember to leave a -1. It's not a completely clean cancellation. It does leave a -1. It's just like saying if you have -5 over 5. Yes, can you cross cancel? Yes, you can, but they leave what? They leave a -1, right? So now we're doing the same thing but with expressions. So, or if you have -15 over 15. Yes, you can cancel, but it leaves a -1, right? The negative isn't going to go away. All right. So can we use the rule here? Well, let's see. Do we have an f minus L over L minus f scenario? We absolutely do. So yes, we can, and the answer is going to be -1. Again, ask yourself, do I have an f minus L over L minus f scenario? Are these exactly the same with the order just being simply reversed, right? See, here a fast one was pulled on you. Almost, but not quite. Because this is x squared, well, that's x cubed. So be careful. Don't go there. Not with this. It's only if those two are identical and those two are identical and you have subtraction going on. These two are not, so we can't say that. So just leave that one alone. You can factor the denominator because it's the difference of cubes, but that's not going to do any good because the numerator doesn't have any reasonable factoring that's possible. So we can just leave this as is. It's already simple. How about this one? We have x squared minus 9 over 3 minus x. Well, we need to factor the x squared minus 9 first. So we get x plus 3 times x minus 3 over 3 minus x. Now we notice that we have a f minus L over L minus f scenario. So we'll go ahead and cancel those, but we have to leave a -1, remember? So we get -1 times x plus 3. Usually we prefer to just distribute that in and leave the answer as -x minus 3. So the last thing we're going to do today is learn how to multiply and divide rational expressions. And the rules are going to be the same as we had for fractions. If you have a over b times c over d, you just multiply across. One of the simplest rules in mathematics, right? Of course, always keep in mind that when we did this before with numbers, we always cross-canceled as much as possible before we multiplied across. So you want to do this once a over b and c over d are fully reduced. And if you have a multiplication problem with fractions involved, remember you can cancel from any numerator to any denominator, including its own, right? So you can cross-cancel from numerator to denominator, but only if the only operation going on is multiplication. So if you're dividing two fractions, you basically keep the same, keep the first one as is, change the division to multiplication, and then you reciprocate the c over d and change it to d over c. Then you multiply across, okay? Now, if you want to know why that's true, write it as a fraction. You have a over b over c over d, right? It's always good to know why things work the way they do. So now notice I can multiply the top and bottom of this fraction by the reciprocal of the denominator. Why? Because you can always multiply the top and bottom of a fraction by the same thing, right? So now watch. Here, c cancels c, d cancels d, right? So the whole denominator cancels out and becomes 1, right? So all you're left with is what's on the top, which is a over b times d over c. See? And that's just basically AD over BC. So A times D over B times C. So in case you were wondering, why does this division turn into a multiplication? Why do we have to flip the second fraction? Well, this is it. It's simple. All right, so when it comes to multiplying two rational expressions, really you're not doing anything beyond the cancellation practice with it. You're going to factor all numerators and denominators as much as possible, and then you're going to cross cancel from any numerator to any denominator as much as possible. So for example, in this one, we can factor the 20y minus 20. There's a common factor of 20. It leaves us y minus 1 times. Now for that one, we're going to factor out a 10. That leaves us y minus 1. And we have 18y down here, which doesn't factor any further. So we notice that we can cancel 9 and 18 to leave us 2 and 1. When you cross cancel, write it prominently above or below. That way you don't, forget it. I see some people, it's as if they're ashamed of the cancellation. They just write a tiny little 2 or something, and that's easy to forget. So just write it nice and prominently. Be proud of it. All right, 10 and 20, they cross cancel. They leave us 2 down here, 1 up there. Now we can cancel these y minus 1s because they're factors. And we know that y and y squared can cancel to leave us 1 and y, right? So what are we left with? Well, see, this is what I meant by make sure you always reduce before you multiply across, because it's so much simpler now. You have y and 1. So just y times 1, which is y. Over, down below, all you're left is with a 2 here and a 2 there. So we get y over 4. Once you start understanding mathematics, you'll be amazed to find that it will become your easiest class. The class that you used to think possibly was your hardest class, you discover that once you stop just believing and just worrying about how, and you shift your focus to understanding and to why things work the way they do, suddenly math goes from being your most difficult class to your simplest class. Think about it. There's hardly any memorization involved, right? So it doesn't put any undue stress on your brain, right? You just have to make sure that you shift your focus from worrying only about how to also why. And then when the how and why interact perfectly, you have the perfect plan for succeeding in mathematics. All right, so same business. We're multiplying still, so there's no flipping of the second fraction or anything like that yet. All we do right now is just factor everything that we can factor and then cross cancel as much as we can. So this you should be able to do. Definitely pause the video and try it. All right, so x squared minus 4 we know is a difference of squares, so we know by now it's going to factor like so. This right here, it is a perfect square trinomial, or you can just factor it out like a regular trinomial. You're still going to get x plus 2 and x plus 2. First times first, first. Last times last, last. Inner and outer give you the middle. This one, also a trinomial type of factoring problem. So x, x. How about -3 and plus 2? What do you think? First times first, first. Last times last, last. Inner, -3x. Outer, +2x. They add up to give you -x. This is, of course, a difference of squares. So we get x plus 3 times x minus 3. Now we cross cancel as much as we can. So we can cancel these right here. Remember, when you have only multiplication, even if there's 10 of these fractions, a billion of them, doesn't make any difference. As long as you're only multiplying and you only have factors, see? Then you can cross cancel from any numerator to any denominator, so even including its own denominator, right? So here we notice we can cancel those. Notice we can cancel this x plus 2 from down here with that x plus 2 from up there, because we know we can cancel from any numerator to any denominator as long as we're careful. So we end up with x minus 2 over x plus 3. And of course, we are finished because we know we can't cancel anymore. These are terms. We never cross cancel from any term or from any part of a term. So we are done. Okay, so here we're dividing. So we remember the rule, a over b divided by c over d equals a over b times d over c, which is going to be a times d over b times c. Never cross cancel anything in a division for our problem until you've turned it into a multiplication problem. Then it's just another multiplication problem, so you can cross cancel, factor, etc. So we get 32x cubed over 20 times 30 over 9x. So now it's just like any of the problems we did a minute ago, the last few problems which were multiplication problems. So we cross cancel if we can. We notice that 3 goes into 9 3 times, into 30 10 times. 10 goes into 10 once, into 20 twice. That should be all that we can do with the 9. Now we notice 2 goes into 2 once, into 32 16 times. The last thing there is, let me use a different color, the x and the x cubed. X goes into itself once, it goes into x cubed, x squared times. So you can do it this way, or if you want to do it using the quotient rule, x cubed over x equals x. Notice there's a 1, 3 minus 1, so you get x squared. Same thing. But if you remember, we did cross canceling of powers of x when they have only positive exponents. Basically, you cross cancel, the resulting value is going to be where the higher power is, and what is its exponent going to be? Just subtract the higher power minus the lower power, or subtract the lower from the higher, and that's where you're going to get the exponent. All right, so let's see what's left. So on the top we have 16 x squared, and that's all there is there. And down below, all that is left is 3, and you are finished. Simple, important, make sure you can handle it. All right, here's the last one for the road. One with 2 variables, same business, but remember, we're not going to do anything until we've turned the problem into a multiplication problem. Go ahead and try it. It's your last one for the day on this video, so make sure you can do it. 8x squared minus 6xy minus y squared over 6x squared minus 5xy minus 6y squared times we're going to move this to the top, 9x squared plus 12xy plus 4y squared, and we'll move the numerator to the denominator. So 4x squared plus 11xy plus 6y squared. Now we're going to go ahead and factor as much as we can. Now that we've turned it into a multiplication, we'll just factor everything out and cross cancel if possible. So let's see. What about 4x and 2x maybe? And 3y and 3y. Let's try that. So let's see. The inner product is going to be 6xy. The outer product is going to be 12xy. So we should be able to get negative 6xy out of it, right? So since we want negative 6xy, we're going to make the larger product negative. So let's see if this works. First times first is first, last times last is last. The inner product is positive 6xy. The outer product is negative 12xy. When you combine them, you get negative 6xy, which is the middle term. All right, let's factor this one. So what about maybe 3x and x? And maybe, let's see. That would not work because we want 6x squared. So let's try again. Let's make that 2x. All right, so we're going to want 5 out of these, negative 5. So what if we try 3y and 2y? Let's see, the inner product will be, remember at first we never worry about the sign, we'll deal with it later. The outer product is going to be 9xy. We want negative 5xy. It looks like we can do it if this is negative and that's positive. So let's make sure first times first is first, last times last is last. Inner product is positive 4xy, outer product is negative 9xy. You add them, you get negative 5xy, which is what you have here. All right, so we'll continue with these. It's all about factoring, isn't it? So on the top, it looks like we have ourselves a perfect square trinomial, right? That's a perfect square, that's a perfect square. So this is a perfect square of 3x. That's the perfect square of 2y. So we want the middle term to be 2FL for it to be a perfect square trinomial. So that 2 times 3 is 6 times, so 12xy. So yes. So this is basically 3x plus 2y times 3x plus 2y. You didn't necessarily have to recognize the fact that it's a perfect square trinomial to be able to factor like this. So that's just a bonus. All right, so for this last one, we're going to factor that. So why don't we try 2x and 2x? And we're trying to get 11 in the middle there, right? So this may not work. Let's just see. So if you have 3y here and 2y here, for example, you're going to get 4 and 6, which is 10. That's not going to be good. Even if you have 3 here and 2 here, let's see, you still get 4 and 6. No good. So we've tried 2 and 3 in both directions. with 2 and 2 fixed here, so we will give up now on 2 and 2 here. So problem was not from the 3y and the 2y, so why don't we try 4x and x. Remember, with these you have to be patient. All right, and then maybe 2y and 3y. Let's see, inner product is positive about 3xy actually, and the outer product is 8xy. We want positive 11xy, which we can get if they're both positive. So we're going to have plus and plus. We do a quick check. First times first is first, last times last is last. Inner is positive 3xy, outer product is positive 8xy. They add up to the middle term, so we factored it correctly. Now it's just a matter of cross-canceling as much as we can. So we notice that we can cancel out the 3x plus 2y and the 3x plus 2y here. These are obvious cancellations here. And we can also, do we have anything else? Yeah, we have these. Let me use a different color. Those, and that's it, right? There's no more cancellation possible. Final answer, 3x plus 2y over x plus 2y. And of course, we really know better than ever trying to cancel anything like those or these, because these are terms and we never cross cancel from a term or any part of a term. So we're basically finished there, and that should wrap it up for us for today. So make sure that you get comfortable with these rational expressions and practice. Stay safe until our next video.